Hey, Honors Chemistry. I wanted to post a brief video on LOL diagrams and energy charts. So I wanted to just make sure this was just a little bit of a review, just in case you were not following along or you were absent. So just a little bit of a reminder, we had some convention with phase energy. We said for a solid, that would be representing with 1 bar, liquid 2 bars, gas would be 4 bars. Today, we wanted to make sure that we always make a distinction between thermal and phase energy. And now we never really want phase energy to be equal to thermal energy. My phase energies will be the same, but I came up with a new scale for thermal energy today. So cold would be maybe 1.5 bars, room temperature would be 2.5 bars, and then we said hot would be 4.5 bars. We wanted to make sure that it was different and distinguished from our solid, liquid, and gas, so we just put like the 0.5 on. So now we're going to construct our own LOL diagram for this scenario. So let's say we have water in the room, and it's placed in a fridge and frozen until it reaches past negative 8 degrees Celsius. So we have several things going on. We have liquid water, and in order for it to get frozen, and it was in the room, so it's room temperature water, in order for it to get frozen, it has to change temperature. So I have liquid water to liquid cold, and then eventually, now that I've got it to be cold, it's got to go from liquid cold to solid cold. All right, so I'm just writing down some ideas of what I have to do. So I have to go from room temperature liquid to cold liquid. And then I've got to go from cold liquid to cold solid. And then this happens at 0 degrees Celsius. And then eventually, I'm going to negative 8 degrees Celsius. So I'm going from a cold solid to a colder solid. So let's keep track of this with an LOL diagram. All right, so I'm going to draw our LOL diagram from scratch here. Okay, we have E thermal, and then E phase, and we're going to ignore ECH. E thermal, E phase, ECH, okay? And so now I want to make sure I'm able to put our bars in for E thermal and E phase. Okay? And we could do this overall. I'm doing an overall. So what is happening, what's ending up happening is we start with a liquid at room temperature. Well, for a liquid, and we're going to say this is the initial. For a liquid at room temperature, if it's a liquid, we're putting 2 bars for phase energy. So there's my 2 bars for phase energy. And then if it's at room temperature, we said that we're going to use 2.5 for thermal energy. So 2.5 for thermal energy. There's my thermal energy. There's my phase energy. And remember, thermal energy is associated with temperature and temperature changes. Phase energy is associated with specific phases and phase energies and changes in phase. Okay? Now, what's eventually happening is I am losing thermal energy twice, and I'm losing phase energy because I'm going from a warm liquid or a room temperature liquid to a cold liquid, and then I'm going from a liquid to a solid. So liquid to a solid means I'm going from 2 bars to 1 bar. And room temperature liquid to cold liquid means I'm going from 2.5 bars to 1.5 bar. And then I'm going from cold solid, which again, freezing point of water is 0 degrees Celsius. So I'm going from cold solid to even colder solid. So I'm going to lose more energy in my thermal. I'm going to lose it twice. So instead of having 1.5 bars, I'm probably going to have like 1 or 0.5. I'm going to do 0.5 bars. So for my thermal energy, I'm going to go to 0.5 bars. And then for my phase energy, that's going to be 1 bar. Right? Because I'm a solid and I got cold twice. So if I'm doing the math here, and this is my final, if I start with, let's say this is 2.5 and 2. If I start with 4.5 bars, oops, we can't see that. If I start with 4.5 bars and I end up with 1.5 bars, it looks like I lost 3 bars of energy. We call that minus 3 bars. So I'm going to represent that if this is my water. If I lost 3 bars of energy, if this is my system, I have energy leaving the system. So I'm going to draw the 3 bars that left the system. Okay? So I have 3 bars of energy that left my system. Q. Now, I'm posting this video because it's a tougher problem that we've been experiencing. Usually, you'd probably have something like liquid room to cold liquid, or liquid cold to solid cold. And this involves, if I change in temperature, I'm changing thermal energy. And if I'm changing phase, I'm changing phase energy. So usually if I had something very simple, if I were to do this quickly, if I want to do an LOL diagram again, let's say I had a liquid at let's say it's 10 degrees Celsius and it's cooled to 1 degree Celsius, right? Just below freezing, all right? Just above the freezing point, right? So I have a liquid and it's at 10 degrees Celsius and it's cooled to 1 degree Celsius. So I'll do my E thermal, E phase, E chemical, E thermal, E phase, E chemical, okay? And if I'm putting in my lines for my thermal and phase and whatnot, right over here. Remember, we're ignoring the E chemical because E chemical is the energy associated with bonds. And we're not making or breaking bonds, so this gets ignored. So if I have a liquid at 10 degrees Celsius, this is somewhat cold. So let's say, since it's somewhat cold, I'll make it 1.5, right? I'll make it 1.5, right? And then if I'm a liquid, I should be at 2 bars for phase energy. That's convention, that's what we've said. And then I'm still a liquid, because I didn't say anything about a phase change, and it's not -5 or anything lower than 0. I'm just a liquid, and I've been cooled from 10 degrees Celsius to 1 degree Celsius. So if I'm changing in temperature, but I'm still the same state, I would keep my phase energy still 2 bars. All right, so that is not changing. Still phase energy of 2 bars. What am I going to do to my chemical energy? Am I going to gain sorry, not chemical. What am I going to do with my thermal energy? Am I going to gain thermal energy or am I going to lose thermal energy? Well, it got cooler. That means it must have lost energy. The only way we could get cold is the absence of heat. So if I have 1.5 bars here, let's just say we're going to have half a bar here. All right, so I start with, over here I have 3.5 bars total, and now I have 2.5 bars total. It looks like I have -1 bar of energy. That means I lost 1 bar of energy. So if this is my liquid, if I lose energy, it's going from the system to what we call the surroundings. So I'm going to have 1 bar or 1 box of Q leaving the system. Okay? Alright, so I'm hoping that video was helpful. Please make sure you rewatch this video if you were struggling with the tough one. I ended with the very simple one, so you could use this simple example in the end of what we typically do. One of our questions in class asked us to go from heating up a liquid to eventually boiling it, and that was in 2 steps. So I decided to show like an even tougher one that involved like 2 or 3 steps. All right, if you have any questions or concerns, please let me know. You could message me in the Remind, or you could comment on this video in the Google Classroom.